All right, let's now see what we should say first. All right, your programming test 1 and written test number 1. Basically, we are finalizing it Monday. You're going to get a result for both. And for your lab number 4, it's going to be, it's released. Sorry, it's not going to be, it's already released. And your programming test 2, which will be about 2 weeks from now. And I want to really draw your attention. It's very important to emphasize, okay? If you look at the timeline, so this is why I really try to release lab number 4 just in time. So you want to make sure you complete the 2 parts in time for your written test number, for your programming test number 2. All right, let me show you exactly what I meant. So if you look at the course calendar over here, okay, there we go. All right, so if you look at that, we are here, 24th, and make sure you submit your lab number 3, your best attempt before the noontime tomorrow. Please, not midnight, noontime tomorrow. And then on the 30th, next Wednesday, so there will be no scheduled test. However, as I mentioned, Andy, one of our TA, is going to be there doing some demo for you. So I would suggest to take the most advantage of it. Number 1, show up. Number 2, Andy is actually going to demonstrate the proof step that are actually required by part 2 of your lab number 4. I would suggest try them out yourself first to see which step you might be struggling a bit. In which case, after the demo by Andy, Shanru will be there as well. You can ask them the question. I think that'll be the best value you can get from the lab. If you choose not to come, it's okay. If you are feeling comfortable after the lab, we'll leave that to you. That's no problem. But I'm just saying, if you're really struggling with lab number 4 to really get through, October 30th is the day to come, all right? All right, I'll try to send you some reminders. I know you guys are busy with all the midterms, but I cannot emphasize enough. October 30th, really important day. And after that, after the due dates for lab number 4, your programming test number 2 will be on the 6th of November. I'm not too sure if we will be able to return the result back to you by the drop deadline, but at least for programming test 2, I would say if you complete lab number 4, understand all the proof steps, it should be okay. Right? I'll give you guys some practice tests as well, a little bit later, maybe early next week. Well, on the halfway through next week. Okay, so that's about the lab number 4 and your programming test 2. And October 30th, all right? All right, guys, any question you want me to clarify about the course? Yes? So, okay, so the October 30th, let me make it clear. It's not just purely Q&A like a PA sitting there and answering your question. We want to make it more interactive. So let me write it down. On October 30th, we'll try to maybe duplicate the same thing for 1:30 and 2:30 session, so you can come either session. It's going to be some demo of lab number 4, part 2, which is about a prover. But I would suggest don't really wait for the TA's demo. You want to try them out yourself first. And the TA is going to demonstrate to you what might be missing. And if you want to interrupt him right away, you can also do that. Okay? So you'll be demo of lab number 4 of part 2, and then followed by some Q&A as well. But mostly demo, I believe. The demo might take some time because you guys may have questions in the middle. Right? Yeah, we'll try to organize the session as much as possible, so you just come and want to get the most value out of that lab session. All right? It may not be so easy to record because Andy may not be so experienced in recording. So please make sure you come. If we can record, we'll try, but we cannot guarantee. So if you show up physically, that'll be the best. All right, any other question about the schedule? All right, if no, let's now do recap. So we're going to do a little bit more in-depth digging into the theories, math. Okay? So from last time, we started talking about sequence, which is important. But before that, let's see the background that we spoke about. So we talk about something called before-after predicates. We're going to talk about it many times, so hopefully you already got an initial idea. You just have to remember the colon equal to that you wrote for event action. It is not really programming assignments. The way you want to think about this guy here is not just like Java assignments. Otherwise, you will get things like the swap program wrong. All right, so we'll talk about this example here to illustrate. If you think about this, this, and this, just like Java assignment, it's not going to be correct. Right? You want to make sure you understand the example there. And then whenever you want to talk about the correctness of your events action, you have to somehow turn this syntax into before-after predicate using the prime syntax. And we'll talk about many more examples coming. So hopefully that can emphasize it more and more. All right, before-after predicate, and also we spoke about pre-state and post-state. The idea is very simple. Whenever you want to have some occurrence of the events, it's more like a state transition. The starting state is called the pre-state. The ending state is the post-state. Because we have no loop concept in each event action, so there's no issue about termination. So you can assume that every event we have, when we do the transition, is always going to terminate, always the case. All right? And then we spoke about if you want to make sure both states in the pre and the post are safe, this is how you think of it for every event. Number one, we assume that the invariants hold in the pre-states, number one. Number two, somehow you want to justify that the invariants at the post-states also has to hold. So what we did last time was simply trying to justify or at least outline what you have to prove very informally. And today we're going to dig very precisely into how you can formulate the invariant preservation as a proof obligation. That's something we got to do today. And once you formulate proof obligation as a sequence, you have to somehow prove it. And to prove it, you have to use a set of inference rules. And that's also something we're going to talk about today. All right, one step at a time. But I would suggest at some point I may revisit this particular effects of the action and see how we may prove it at some point. But for now, it may be maybe a little bit too complicated. We can do that a little bit later. All right, so that's the swap specification. You can review the example to really make sure you understand why this is not correct, but this is correct. Maybe too simple to be true, but that's really the only way to do it. And that's just some general formalization about invariant preservation. And that's important. All right, let's start from here. We introduced you about the syntax and semantics, the meaning for sequence, right? And very quick. So we got turnstile. And sometimes you might write a sequence horizontally, or sometimes you might write it vertically. Doesn't really matter. Each one is correct. It's a matter of style. So to the left of the turnstile is something called hypothesis or assumption. To the right is something called goal or conclusion. It is something we want to show to be provable. We want to say, given that hypothesis is actually true, we want to show that this goal is provable. If essentially, we are showing this implication relation. Right? So logically, nothing new. We're just using a notation that's going to be easy for us to make a series of steps for proof. That's something we'll see. Very soon in today's lecture, we're going to see another notation that kind of looks like turnstile. But that one's going to be something totally different. But I just want to give you a little bit look ahead, some heads up. But I'm going to also compare these two notations today, because we're going to use these two quite closely. You don't want to mix one with the other. And one more thing to say, you got to remember for H and G, each one individually can just be a set of predicates. Okay, multiple ones. Right? That's also by definition. This is one example here. All right. This is actually one of the proof obligations we have to discharge a little bit later today. Right? How do we read it? We are saying that we are given these assumptions. We know that D is a natural number. N is a natural number. N is bounded by D. Given this assumption, we want to show that N plus 1 less than or equal to D is provable. Whether we can show it or not is another story. But that's our goal. We want to show it. All right, so that's how you read the sequence. And don't forget, if the sequence here, the hypothesis is simply empty, that means this part here is actually true. All right? All right, and then I think this part here, I should say, I did a little bit in a rush on Tuesday at the end. Let's do some part again. So I think that's really important. This is kind of the exercise we have to do quite many times, and that's something I would expect you to do optimally, maybe in the written test too and the exam. So let's do that properly. Okay? Let me do it again. I want you to first of all look at this sketch over here. If you look at the slides, let me show it to you. So here I say, here is a sketch. That means it's not exactly precise about what should be included. Not exactly. Maybe about 80%. Not exactly 100%. To really see the 100%, we need to have one page to really go over some notation. Could be a little bit dry, but I'm going to get it through quickly. But for now, let's get some intuition. Now, if you see the INV over here, okay, so this is about the rule. Proof obligation rule. So INV here is the proof obligation rule. Proof obligation for invariant preservation. We want to show that by making the transition of a single event from pre-state to post-state, the invariant should be maintained. That's what we're trying to show. And this is what we have. We have a turnstile over here. What we want to prove as a goal is here. We want to show that the invariance should be satisfied at the post states, meaning that it's maintained. Right? You can see post state here. That's really important. That might be the only part that's a bit tricky to get right, but that's something I will do carefully this time. And what can we assume in order to show that the maintenance is provable? We got to include several things. Number one, we got to include all the axioms. We got to include the same invariants, but those invariant is assumed to be satisfied in the pre-states. The only thing you have to remember is whenever we talk about pre-states, we really mean some variable v, unprimed. When we talk about the same invariants but satisfying the post-states, you simply put every occurrence of v to be v prime. That's the principle. No matter how complicated invariant might be, we'll see that. And finally, in order to really have the events occur, you want to make sure the guard is true so that the event is enabled. That's a very important assumption. Whenever an event actually occurs, the guard must be true. If the guard is not true, it's simply disabled, right? All right, so that's about some interpretation of the sequence. Let's now try to do some routine work to see how we can formulate this particular model into the proof obligation, okay? Let's now take a look. Let's start with something simple. I will first of all start with the axiom. So the axiom is here, so which will contain just this single axiom, just this one here. All right, so I'm going to get D is a member of natural number. That one's easy. And then I want to get the invariance and plural, which means including all the invariant conditions. In this case, we got two of them. And by the way, if you look at this convention here, if you look at the 1 and 2, so these are the indices we are using to index the event. Number 1, number 2, number 3. Straightforward. So these are the indices of the invariance. Another thing to note, the 0 over here is about a model. This one tells us we are dealing with model M0. So later on, when we get to M1, which is a refinement of M0, we're going to see 1. All right? Just to know the convention here. All right, so now how do we do this one here? Simple, just copy them. Because now we're talking about pre-states. So just a variable without any prime. So it's going to be n is a natural number, and then n less than or equal to d. Okay, just separate them. The new line here is implicitly a conjunction. Implicitly. Let me write it down. New line in hypothesis section is implicitly a conjunction. Okay, I will try to write another note in just a moment. We haven't done yet. And this one here is about the guards of the events. So here, when we say the events, there are two possibilities. It could be either for ML out or it could be for ML in. So that means this proof obligation tells you you're supposed to generate separate proof obligation. One for ML out, the other one for ML in. All right? But for now, we're just going to do one of them. Let's say for this example, we just do ML out. And for ML out, the guard is missing. It will be as if it's actually true. So it is as if when we say when, true. So I'm going to put true over here. All right, so that's about the hypothesis. And then we're going to have the turnstile. All right, so before I forget, I just want to make one more note. If you look at what we have over here, the whole thing, you can see we got a new line here, a new line here, a new line here. They are implicitly just conjunction. It would be logically equivalent if you simply have only a single hypothesis, just one predicate is possible. So this one here is equivalent to, you just say D is a natural number, and N is a natural number, and N less than or equal to D, and true. The same. However, later on we'll see, if you try to have a big conjunction as the hypothesis, it will make the proof so much harder. So I would say, if you want the best strategy to really get your proof easier is to separate all the hypotheses into different lines, as we'll see. That's how the inference rule that we're going to see will be defined. That's just an aside. But logically, they really mean the same thing. All right? Now, finally, this is the important part. How do we formulate this guy here? Invariants satisfy at the post states. All right? When you are not so familiar with such construct, which I believe most of you are, I would suggest always start with something intermediate. It'll be easier for you to actually get to the ultimate answer. Always just remember, when we talk about post states, all the variables should be prime. So let me now, first of all, copy the invariants. So these are the invariants. Let me copy them down first. It'll be N is a member of natural number, and also N less than or equal to D. Right? That's all the invariants combined together. And since I talk about post states, I'm just going to put a prime at every occurrence of N. That's a very critical step you want to do. Don't miss anything. You copy the original invariants. Usually in the invariants, you will not put any prime. But once you want to get a post-state version of invariants, add prime to every variable. This will be the intermediate step. And then, let me box this and say star. Okay, let me work from there. If I got N prime is N. Also, N prime is less than or equal to D. You cannot simply have a sequence where you got a prime. It wouldn't be acceptable. It's got to be without a prime. The only way to get rid of the prime is to look at the before-after predicates for each action, right? So now we are talking about ML out. So this is the event we are considering right now. And if you look at its events action here for ML out, this becomes operator, but we can easily turn that into the before-after predicate. So the before-after predicate is simply M prime equals M plus 1. All right? Well, if you want to think about it, just turn the left-hand side into the prime version of the variable. The right-hand side stays the same, right? Before-after predicate. So once I have got A here and B here, you will know how to do the substitution. Right? Based on A and B, I can now say, rather than M prime, I can say M plus 1. And M plus 1 less than or equal to D. Several steps over here. Step number 1, let me recap. Step number 1, okay, why are we doing this? We want to work out logically what's really the invariance that's actually satisfied at the post states. Step number 1, copy the original invariance. Step number 2, prime each variable. Step number 3, you want to look at the before-after predicates of the events, of the relevant events. In this case, it tells you M prime should be equal to M plus 1. So you can replace every occurrence of n prime here just by n plus 1. And in this case, you get rid of the n prime. And what we have over here actually makes sense. It tells us, if you compare, let me write it down here. So let me copy this back. So this is the invariance at the post states. So this is the invariance at the post states. And if I put it back here, n plus 1, n. And n plus 1 less than or equal to d. Now I want you to compare invariant in the pre-states, invariant in the post-states. They are basically the same structure. The only difference is what we used to say should be a natural number is n. But now in the post-states, n plus 1 should be a natural number, simply because the n here has been replaced by n plus 1 by the updates of the ML out. All right? And what we used to say has to be less than or equal to d, and now has go from n to n plus 1, simply because n has been replaced by n plus 1. All right? The same principle is going to apply for all the invariants we're going to do for the post states. I would say this will be the most difficult part to really get right whenever you want to formulate invariants, formulate a proof obligation. Just make sure you don't put any prime here. That's wrong. That's only intermediate. All right, any question? We good? All right. And this is only the first time we're doing this. We're going to do many times. All right? At least another 1 or 2 times today. So that's good enough for the first time. Any question about this? Yes? You mean this one? PO? BAP? Oh, sorry. There we go. I should have explained. PO, proof obligation. And VC, sometimes people also say verification condition. You can also use it if you wish. But I think most of the time, I'm simply going to say proof obligation. Yes? Why we are priming the variables? Yes. So the very reason is, if you look at the sequence structure over here, we are assuming that invariants satisfy in the pre-states, or put it in this way. Make it more visual. Think about you're doing some transition. Let's say ML out. So ML out is going from this to this. And we know that this is, and this is the post states. What we want to make sure is, assuming that the invariance is satisfied in the pre-states, we want to make sure, given that ML out is enabled, if ML out takes place, the post states for ML out should maintain the invariance. Invariance should not be violated. The way to express that is to say, I prime is actually true. I prime simply means you got to prime all the variables. Because when you get a prime version of the variable, they denote their values in the post states. That's why. Okay. Yes, question?
Yes, so if the guards always have to be true, right?
Uh-huh.
Why do we have to add it to the proof obligation?
Okay. So I think in this special case, our initial model started with the ML out without any guard. But since the proof obligation rule here tells you should really include the guards, of course, if you do some logical simplification, we know that P and true is equivalent to P. You can get rid of it. But just in the initial sketch, we can include it just to be explicit that this is the guard for this event over here. Mm-hmm. On the other hand, let's say if you got something like the guard is being false, meaning that event is always disabled. In that way, you're going to have a false over here, and then consequence is going to be very funny. Because given that new line is implicitly conjunction, if you got false over here, everything is going to be false. And false implies anything. So you don't really have anything to prove. Right? So you got to be very careful. All right, that's only the start. But we'll keep emphasizing, keep repeating. All right, guys, I'm sorry. The next 10 minutes is going to be a little bit dry. But we'll get it through. Okay, this guy, this rule over here is mainly just about informal sketch for you to get an idea, but we are not being very precise about how many proof obligation exactly you're going to generate. Now we want to be more precise. To really make it more precise, we have to use certain notations. And that one there, I'll try to summarize in a single page. And I'll try to do that as quickly as possible. It's dry, but we need to do it. All right, so let's now take a look at the slides. On the slides, everything we have already said, that's kind of informal meaning for the proof obligation. And we got over here. All right, so slide 18 is going to be all the components that we need to know. You don't necessarily have to write them out yourself, but at least when you look at a proof obligation rule, you have to know, based on the proof obligation rule, which will use these components, how you can go from there to generate the proof obligation. That's why we're introducing this. All right, let's go one by one. They are not hard, it's just a bit dry. All right, let's go one by one. Let's now start with constants. All right, so now let's go one by one. So we are going to use this model over here as a running example. All right, so we start with the list of constants, C. All right, the way you can see that the constants is exactly here. It's going to be a sequence. So we can see by is defined as. So this symbol here, you may have seen that before. It simply means it's defined as. All right, and now it's going to be a sequence over here, a sequence containing just D, only one constant. So angle brackets over here is our notation for sequence, right? Comma separated, but now just one. Okay, just constant. And the next one is going to be axiom. How do you read the axiom? Axiom here, you can think about, is more like, you can think of it, it's more like a function on constants. A function on constants. Meaning that given a list of given a list of constants, I'm going to give you some expression for the axiom. All right? And for simplicity, we're just going to include the label of the axiom so we can refer to them. So now, given that we got only one axiom over here, so the way to do it would be, we just say the list of axiom, so A, and in this case, we only got the constant D. So our axiom can only be defined in terms of D, in this case, right? Nothing else. Can only be your axiom cannot be defined in terms of the variable, but invariant can. All right, that's why you'll see the difference. All right, so this one is going to be just, we're going to say the label. Axiom 0, model 0, and then axiom number 1. Right? A single one, just label. Let me emphasize again. The reason that you're seeing A parenthesis C, you're basically saying the axiom is basically a function taking as input the constant list. It's going to return back to you a list of axioms. That's what it is saying. All right? All right, and then the next one will be variables. And here we got to distinguish between the pre-state and post-states. So I'm going to say V here. You can see V here. And also we got V prime. And you can see V correspond to the pre-states and V prime correspond to the post-states, right? Let's be very careful. So you can see for the same variable N here, we have the pre-state value, which would be just a list of variable, which is N. All right? And similarly, we also got a list of post-state variables, V prime, which in this case will be N prime. As easy as that. Okay? And let's make some annotation. This list over here is just the pre-state value. And let me just say pre-state. That should be enough because pre-state contains a list of variables. And this one here is the post-states. Okay? Okay, so far so good. We're almost halfway through. And the next one there, let me see if I can just enter a new line so you wouldn't be so troubled by what I wrote over there. There we go. That's better. All right. The next one is invariance. Okay, let me highlight it. Okay, invariant here, around the bottom there. Hopefully you can see that. Similarly, invariant is a function. But now, this time, rather than taking just constant, it's going to take constant for sure, but also takes variable. What this means is, whenever you're trying to define your invariance, it may involve both the constant and the variable. For example, you can see this invariant here, it involves both the constant and the variable. Right? That's what it means. And let's now just write it down. So the invariance here, this guy here. As you can see, the C here, the constant, is the list of constant, which is D. And the V here is the list of variables, which is V. Okay? Oh, sorry, not V, N. Of course. N here. All right? And then we're going to say invariance I, which will take constants and also variables, is going to return a list of invariant conditions. In this case, for model 0, we have two invariants, index 1, index 2, right? Two of them. So what I will do is I'm going to say we have invariant V 0, 1, and also invariant V 0, 2. Two of them, labels. All right? However, there is one more notation which you will see very often in the proof obligation rule, which you will see. So if you only say I, it refers to all the invariant conditions. Doesn't matter how many you have, just all of them, all together. There is another alternative. For example, you might say I here, but I might say 1. This tells me just give me index 1, invariant condition, just 1. And then index 1, and then we also got constants, we also got variable. And this one here is just going to give us invariant 0, 1, which refers to just this one here. All right? Easy, okay? This indexing notation is especially important because when we talk about invariant preservation, if I may, let me just skip very quickly for you. All right? If you look at our invariant sketch over here, so here, this is only informal English. But when we try to prove invariant preservation, we don't want to prove all the invariants being preserved at one go. We want to do individual invariants. So we want to do index 1, index 2, index 3, all individually, a separate proof obligation. That's something we'll see. So that's why this indexing notation is very handy, which we'll see very soon. All right, almost done. And we got the guard over here for events. So this one tells you every event guard may refer to the constant. In this case, D. Also, they may also refer to variables, N. Okay? For example, what will be the guard for in and out? This one, pretty straightforward. It's simply just true. So you would say the guard for this particular events, which will take D and also N potentially, but this one here is simply just true. Just that. Okay? Think about the guard here is more like a function that's going to take list of constants and list of variables. It's going to return some predicate. But this predicate here is like extreme, just true. But later on, we'll find that our very initial model is problematic. We should really add more guard to the action, to the events. We'll see that. And very quickly, for this event over here, also there's one guard, which is also true. So the guard for this event, which will take D and also N, that's also going to give you true, the same. All right. Now, here comes a very important one, E. All right. This one stands for the effects of the events. So the E here stands for the effects of the individual events. And when you specify the effects, for example, this is the effects. And this is also considered as an effects. All right, different events has different effects for their actions. All right, events action here. And whenever you want to define the effects for the events, you can use both the constant or the variables, or both. You can do that. That's not a problem. So you would say that the effects of D and also N is simply equal to N plus 1. And one thing is a little bit subtle. The reason that we are putting N plus 1, this effect over here, in a sequence is because sometimes you may have multiple variables. Right? For example, if you remember the swap program, let me put it right here. If you just remember that one there, let me put it right there so you will see just one more. If you remember for the swap, and then we say the correct answer should be begin and end, we say X should become Y, and Y should become X. Right? That's what we said earlier. And what will be the effects for this particular event? So now for this particular event, you would say the effects of, let's say for that particular program, we don't have any constant, just variable X and Y. Effects of empty constant list, but we got X and Y variables. And then it should be equal to, now, guys, what should it be? What should be the sequence of the effects? We're going to collect basically the value on the right-hand side, the Y and the X, like how we collected N plus 1 and N minus 1. All right, just like that. All right? It's going to be just a sequence over here. It's going to be Y, comma, X. So the order is important because when we get to the very final one here, so we're going to say the post state is going to be equal to the effects because the order must be correspondingly, must be correspond to each other. You will see. Okay? So here, that's why we've got to say YX rather than XY. Okay? Final one. How do we interpret this? This one here is about the before-after predicate. Before. Oh. This one is the before-after predicate for each individual event. And the way to define that goes like this. We take the list of variables in their post states on the left-hand side. On the right-hand side, we're going to say what's their corresponding value should be in terms of the pre-states. Okay? V prime are all the post-state variables. And the E over here is about the values in terms of the pre-state value. All right, let me do one final example, and then we're done with this page. This might be the driest one for today, but we're almost there. As I said, the reason that we have to do these notations is because when we look at the proof obligation, either from the slides or from the textbook, they really use this notation. That's why we've got to understand it first. Okay? All right, final one to illustrate. Now, how do we figure out the before-after predicate for ML out? How do we figure out the before-after predicate for ML in? Right? Let's now do that. Okay? So let me now try to do this one here. I'll put it here. Based on the action here, what's really the before-after predicate here? By definition, it's going to be the list of prime variables in the post states. So it's going to be just M prime. If you remember, m prime is exactly v prime from before, right? That's something we did earlier. And then we say that there should be some equality between, so I'll put an equal here. And this will be the effects, which we work out already. That should be m plus 1. What does this mean? This means in the post states, we have one variable called m prime. Its post state value should be equal to m plus 1 and just correspond to this. All right? Similarly, if we look at the action over here for MLN, similarly, we're going to say before after predicate will just be m prime, post state value will be m minus 1, right? So that's a before after predicates. And I just noticed that I didn't write down the effects for that. I'll write it down first. The effects of constant and also variables will be equal to m minus 1 in this case, right? So you can see the corresponding m minus 1 and also m minus 1. All right. A final question for you, and then we should be good about this page. You can just take a look maybe after today's class and just get used to the notation. We're going to look at this notation very often when we look at the proof obligation. How would you express the before-after predicates for the swap? That's the final one I would like to talk about. How would you do that? Well, of course, to do it, you have to do this format here. What's v prime? Should be x and y, right? So now it should be, let's put it here, v prime should be x prime, y prime. That's the list of variables. And then we say that should be equal to the effects, which we work out already, yx, y, x. And as you can see, now it does have the swap. X prime corresponding to y, and y prime corresponding to x. That's exactly the swap. Right? That's a before-after predicate. But don't get me wrong. Whenever you're asked to write out a before-after predicate, you should still write the normal notation, like a m prime equals m plus 1. But here, we're just using the notation that's actually based on the proof obligation rule. It's different, right? Whenever you're asked to write down any before-after predicate, you should just do what we did last time in the class, right? Don't get confused. All right, any question? We're good? Good. That's awesome. All right, I think it's now time to take a very short break. And then after the break, we're going to apply this notation here and apply to the real proof obligation. That's what we do. Okay, why don't we take a short break and take a mobile device ready. All right, just before we get back to the proof obligation, I think you guys might be having a common question about one of the things in lab number 3, which is about using a choice predicate. I'll show you very quickly about what you should do. So if you go to the event B summary documents very quickly, if you go to document number 3 is what you have, oh, sorry, not number 3. Number 4, the choice by predicate. That's what you want to look at. I'll give you one example. So the syntax goes like this. It's going to be colon and vertical bar. It's going to be some variable list separated by comma, and then some predicate on the right-hand side. Okay? I'll give you one example here and some principle that you can follow. Okay? Colon, vertical bar. So it's called choice by predicate. Yep, over here. So it's going to be something like the colon vertical bar. Let's say we take the swap specification as example. All right? On the left-hand side, you want to think about what variables are going to be changed. Change list of the variables. In that case, it would be x and y, for example. Right? And then on the right-hand side, it's going to be a predicate, a little bit like how you specify set comprehension. And here, we want to characterize the post-states values, which means you got to use the prime variables. Post-state characterization as a predicate. That's why it's called choice by predicate. Right? So you might say x prime equals y and y prime equals x. So in your lab number 3, you have to maybe change b or r, whatever. That's kind of indicated by the instruction. That's something you will have to do. So the principle is, on the left-hand side, again, you're going to list all the variables that's going to be changed by that particular event action, all the variables involved. On the right-hand side, you're going to state as a predicate what's going to be the post value in the post states for those variables.
So will we use x prime condition or will we be using x equals y equals?
We're going to use x prime. So this is a different one, right? You can think about doing this will be as if we say x becomes y and y becomes x. It's similar. It's just different notation.
Okay, so it will understand if we're writing x prime as a post-state value.
Yes, exactly. Yeah. So you can think about this guy here is pretty much the before-after predicate, right? Part of it, right? Yeah. Yeah, give it a try, and then before the deadline, make sure you submit, and then when we give out a solution tomorrow, take a look. Maybe I can go over some of it, maybe on Tuesday, right? It can be also beneficial for maybe not necessarily the programming test. I don't think it's going to be very relevant, but maybe for the later written test or the exam. Okay, we'll go over that. All right, very good. All right, let's now go back to what we have to do. Now, let's take a look at this first proof obligation. It's a very fundamental one, okay? And before that, let me just see if there's any slides I forgot to show. Let me be sure. We got, okay, this is what we have gone through before the break. All right, you can take a look. Everything has been set. Okay, so what we need to do now is we have to specify the rule of the proof obligation. Based on the rule, we can apply to our specific model and generate all the proof obligation. And this is our first one. All right, so then, okay, that should be the one to start. And you can see this one is not as informal as the earlier sketch that we did over here. But they're basically talking about the same thing. But now we're just being more precise what you really have to include. All right, let's now take a look. This one here, axiom, defined in terms of the constant. This one here, does it include only one invariance or all the invariants? All the invariants, right? It's not indexed. And invariance is going to be defined in terms of the constant and pre-state values, no prime. All right? It's important for you to see this right away. This one tells you it's going to be all the pre-state values. All right? And then over here, we're going to have the guard of some events. So G here, let me put a star here because it's going to be relevant to the question I ask you over here, which you're going to solve together. Okay? So G here refers to the guard of some events. In this case, it could be the guard for ML out, or it could be the guard for ML in. It could be either one. And the guard is going to be defined in terms of the constants and pre-state value without a prime. And so these three are the hypothesis for the sequence, right? And then here is very important, right? Notice that there is an index I here. That tells you you only put a single invariant condition as the goal. And we got two possible ones here, either this or this. We're going to discharge them separately. All right? So I here, I can be 1 or I can be 2, depending on which one we're talking about. All right? And each invariant condition may be defined in terms of the constant and also the effects. And effects basically will be the post-state value in terms of the pre-state value, if you think of it before the break. So now if I want to figure out, over here, if I want to figure out the post-state value for n prime, I can simply go for the effects for the events. In this case, n minus 1, right? Just very quick review, but you can refer to it later. So now this one here is going to be the effects of the events. The effects of the event. And then, now for this one here, I think that's good enough for now. And here is a question we want to consider. Based on this rule for proof obligation, how many proof obligation or verification condition do we need for this initial model M0? How many? That's the question, based on this rule. I'll give you slight hints. You want to really consider this one here, and also this one here. There are two things you have to consider. I would say star and also star star. These two combined together should really tell you exactly how many proof obligation you will need to generate for this model here. Anyone? If no, I can tell you the answer and figure out. It's only your first one, so I wouldn't be so mean. All right? Okay, let's now work out together. Let's look at the star. The star tells you you have to put some guard, the guard of some events. Some events. That tells you there are two possibilities. It could be the guard for ML out, or it could be the guards for ML in. So we got two possibilities here. And of course, if you got more events, you got more proof obligation accordingly, right? And what about star number 2 star? Here we know that invariant condition, if we want to consider each one of them in isolation, we got either 1 or 2, right? Also, we say some invariant condition. Which is going to be either invariant 0, 1 or invariant 0, 2. Oh, by the way, when I say or, I don't really mean disjunction. I just mean this or that, right? That's really what I meant. Just in case you're wondering, why do we need or? Why not implies, right? All right, so given these two dimensions, we can figure out exactly how many sequence we should really generate. Each sequence is a proof obligation. All right, so now in total number of proof obligation will be 4. 2 times 2. Okay, if you like, I can make it even more explicit for you when you review. 2 times 2. For example, if we got 3 events and 4 invariant conditions, we need 12, and etc. That's how rodent works too, behind the scene. Yes? Oh, those are actually there's no actually like a combination issue here, because here when we say we want A here, A simply means all the axiom. Ci here means all the invariant condition, which means for every possible guard and invariant condition combination, you're going to include all A and all I anyway. Okay, that's a good question. But the reason is here, this is some scope of combination here, because for G here, it can be for either events. You don't know which one events, right? And also this one here for invariant condition, you also don't know which one it is, right? So that's why we can have some combination here. All right, so now for this page here, I'm gonna just talk about exactly which 4 sequence are gonna be generated. But we'll work out a sequence in the next page. But let's see how we can generate them. So let's put it here. So there is a naming convention that we're also going to see in the slides in the textbook, but mainly the slides. So proof obligation number 1. So we first of all put the events. ML out. And then we put the invariance condition, invariance 0 and 1. And then we put another IMV. Right? That's the whole label. Right? How do we interpret that? And of course, this one here is the events. And this one here is the invariant condition, a single one. And this one is more like the nature of the proof obligation. It has to do with invariance. Later on, we might have something to do with deadlock freedom, something like that, right? So for now, this has to do with the nature of the invariance, the nature of the proof obligation. So the first proof obligation we have is ML out. Oh, maybe use yellow. That might be better. ML out, invariance 0, 1, invariance. Okay, what about the second one? Maybe also for ML out, but we're talking about another invariant condition. So let's enumerate it. So PO2 is going to be ML out. And for the same events, but we're going to say invariance 0, 2, and then slash invariance. Right? You can see this one here is also for ML out, but it's for a different invariant condition. One of them is condition 1, the other one is condition 2. But both of them are of the same nature for invariant preservation. And up to this point, it should be quite obvious to you what the other two should be. Right? I'm going to put that as an exercise for you. And you can check out the answer on the slides. So exercise for you. You want to put out the label for PO3 and PO4. Right? 4 proof obligation in total. Apparently, the other two should be relevant to ML in. Question?
What are the guard of ML out? Like, isn't that the same as invariant 1?
So here, yes. So you can see the guard over here simply tells you the guard of some events. When we say some events, what are the possibilities? It could be either ML out or ML in. So when we actually get to, for example, PO1 over here, we're going to include the guard for ML out.
Okay, so in this case, we didn't have it.
We didn't have it, not yet. Yeah. So here we just talk about how we name the actual sequence that we're going to generate. And when you get to, for example, PO3, and that one will have to do with MLN. In that case, for the guard, we're going to include also its guard, which happened to be true in this case anyway. Yeah.
So if we have, let's say, one guard and ML out, so the total number of guards for some events will be 3.
Sorry, say it again.
So if we had an event, if we had a guard in ML out or
Yep.
a guard in ML in, so the total number of guard for some events will be
No, not that. So here, you can think about the guards. We don't talk about individual guard. We talk about all the guards for that particular event. Maybe that's a confusion. So here, the guards of some events, all the guards. All right? It can be anything, yeah, depending on what's the constraint for that event, right? Yeah. Yes?
So when you're writing the publication, are there any cases where you're able to, let's say, prove the first one, but you're not able to prove the second or the third?
You mean,
You have to write all proof of the
yes, exactly. So you're going to write out PO1, PO2, PO3, PO4, which I will leave PO3, PO4 for you as exercise, but we'll see them anyway in the later pages. The idea would be, so here's the progression. We first understand how to interpret the proof obligation rule, which is here. That's why I kind of spoke about the different notation. Once we have seen this, we can work out how to generate the total number of proof obligation, in this case 4. And then in the next page, we're going to see exactly what they are. Once we see what they are, we're going to learn about inference rule to discharge them. That's what we do. We've got 15 minutes to do that. We'll see. Maybe. All right, next step. We know that there are 4 proof obligations. Let's now generate 2 of them. The other 2, exercise for you. All right? So let me just use PO1 and PO2. All right? So PO1, so it would be proof obligation. So PO1. It will be ML out. Also invariant 0, 1 in. Also we got PO2. In this case, also ML out. That one there, we are talking about invariant condition 0, 2, and then INV. All right, let's talk about these 2. And for the other 2, exercise for you. Again, you can find the answer in the slides. Yeah, I definitely recommend you do really try to figure out how to do PO3, PO4, because you got to do that quite a lot. Okay? Question? The nature means we are what's the nature of the we're trying to prove something about can this particular event maintain the invariance when we take the state transition. That's a good question here. Let me write down explicitly. When I say ML out, invariant 0, 1, and also INV. Right? So this one here, I really mean that the proof obligation is related to whether or not taking a state transition of events ML out can preserve or maintain. You can say either way. I'll write down both. Preserve or maintain invariant condition 0, 1. Only one of them. That's what we're saying. Mm-hmm. Yes? No, not really. So here you can think about, since the nature is about proving or the maintenance of the invariant, so that's why we're saying this is a specific invariant. We're trying to prove that it is preserved. We never have to do anything with the guard itself. But we'll do, technically, something about deadlock freedom, which we'll get to later. Yeah. All right, I think that's a good question. It's fair to ask. I think it's good to clarify that. All right, let's get back here. Now, how do we formulate this condition? We'll try to do these 2, and then we can do a little bit of inference rule. We'll see. If we can, we'll do it. Otherwise, Tuesday. All right. I think the idea will be in the very beginning of the bridge controller mathematical part, we go a little bit slow. But once we get through the very initial model, we will be seeing all the necessary steps to prove a model. So we can be a little bit faster when we get to later model. Okay. So that's the idea. All right. PO1. And we're going to follow this rule. So later on, an easy question, I would say, you might be given. I'll give you the proof obligation rule. I might give it to you. And then I'll say, given this model here, now formulate this as a secret. All right? That one should be easy to do. Let's do one by one. First of all, what about the axiom, AC? And I can refer to just this axiom here. D, N. I'll do these 2 in parallel. This one here, also D, N. So you can see exactly the difference between these 2. And then we also got invariance in the pre-states, right? Also only V. That one there is going to be entire thing. So we're going to put N natural number, also N less than or equal to D, N natural number, also N less than or equal to D. All right, that's good. And the guard. And since we are talking about ML out in both cases, it will be the same guard that we're talking about. But I think once we get to slightly later stage where we're going to get different guards for ML out, ML in, it will be more interesting. But for now, let's live with it. For ML out, we know that implicitly it's simply just true. Okay? So I'm going to put true over here for ML out guard. Also true over here as well. Okay? We are good. And of course, we got a turnstile. So far, we work out the hypotheses for both proof obligation. Again, each proof obligation is a single sequent. Right? Right, finally, let's see how we can work out this guy here, right? This is where we did one single exercise before the break, but let's do it another 2 times. Okay? Number 1. Here, we got to work out, so here you can see I, it will be 1 in one case, and it will be 2 in the other case. Right? What about the 1? And I would suggest, again, do the intermediate step. For the 1 case, you're going to do n prime is a member of n. This is not the final answer just yet, but it's a sketch. Okay? Similarly, for the second one, number 2 condition, is going to be this one here. So it's going to be n prime less than or equal to b. Intermediate answer. And how do we work out n prime and define that in terms of the pre-state value? We got to look at the before-after predicate. So in this case, we're going to look at the event action over here. We know that n prime is equal to n plus 1. So n plus 1 here should be used to replace n prime. So let's say here, n plus 1 over here. Okay? So now I'll simply replace this by n plus 1. Replace this by n plus 1. So the final answer, but I would say don't really write this just as final answer. It's not as nice. You can kind of erase this part here and then just put this up, right? You see what I mean? So the final answer should be n plus 1 is in n plus 1 less than or equal to d. You don't necessarily have to rearrange the term. For example, if you don't want to say n less than or equal to d minus 1. You can do that, but it's not necessary. All right, that's pretty straightforward, but I'll suggest give some practice about the other 2. Exercise P03 and P04. What should they be? It's just 2 sequence, right? That's your exercise. And you can check the answer on the slides. I got 7 minutes. I would suggest we have some very gentle introduction to inference rule. And that will continue there Tuesday. Okay? 7 minutes. No more, no less. All right, so here is the thing. It might be easily confused with the sequence. So that's why it might be good to talk about it before the weekend. All right? So how do we understand this? Number 1, notice that this is not turnstile. It's a horizontal bar. All right? And we got something here, we got something here, and we got some label here. All right? Let's talk about what it is supposed to mean, and then I'll give you some example, and then if time permitted, I'll give you some contrast. If not, Tuesday, but we'll see as much as we can do. You can also see the slides. It also summarizes what you should know about a inference rule. I'll show you which slide you should really go to. Yeah, exactly here, right? Inference rule. And again, inference rule is different from sequence. They are related, but not the same thing. Okay, let's talk about what the syntax really means. Let's start with the A. A is the antecedents. Antecedents as in the implication, right? Antecedents. Now I'm going to tell you right away, antecedents can be a set of sequence. I'm not saying predicate, I'm saying sequence. All right, it's very important to notice that it's a set of sequence, even though you can understand each sequence as a predicate, like an implication. All right, a set of sequence. And the C here is called a consequent. Consequent. And this one here is a single sequence. A single sequence. Right? Let me emphasize single, very important. A single one. All right? And I'll give you one example right away. So this, just one more thing before I give you an example. This is the name of the inference rule. Of the inference rule. Whenever, inference rule is going to be the individual step for justification. Every time you use the inference rule, you have to give its name. Okay? Let me give you one example right away. Let's now this guy here. Horizontal bar. Oh, by the way, there's no vertical version for the inference rule. Don't write a vertical version. It's wrong. All right? It's going to look funny anyway. Okay? All right, so now there is a rule called MON, standing for monotonicity. But I'm going to talk about this in more detail. We're going to use this a lot. Monotonicity. All right? And it looks like this. H1, H2, turnstile, G at the bottom. And then we got H1, turnstile G at the top. This is an inference rule. Looks pretty weird. All right? Let me give you one example, just syntax right away. So you can see here, A is like this. And this is, so you can see this is a single sequence. And this is also a single sequence. I said this can be a set. Indeed, it's a singleton set. A set containing only one sequence. So that's okay, right? Sometimes you might see a single sequence over here, like you got two separate sequences at the top. That's something we'll see for sure on Tuesday. All right, I got 2 minutes. Let me say the following. What's the full meaning? Full meaning for that. Let me just write it down. The semantics for a sequence, an inference rule is like this. We say that A implies C is equivalent to true. All right, so that's a formal meaning. So we're basically saying A implies C is something that's already provable. We don't need to prove it. It's something you're given. All right, that's a formal meaning. And I'll compare this with the sequence, maybe on Tuesday. But let me say one more thing here. How do we interpret this? This is important. You're going to interpret in the same pattern for every inference rule. We're going to see in total about 20-ish by the end of the semester. Not too many, but you need to know each one of them pretty well. Okay, let's write down the meaning, and then we should be good. So this is saying the following. To prove the consequence over here, to prove H1, H2, turnstile G, in order to prove this single sequence, it would be sufficient to prove the one above. Okay? It is sufficient to prove H1 turnstile G. So what I really want you to get used to maybe before Tuesday, I think it's a nice break before Tuesday, to say, we always remember to prove the bottom, it is sufficient to prove the top. Always remember this order. Don't get it confused. All right, I think it's now a good point to stop, and then Please finish lab 3 as much as possible. Make sure you make progress on lab number 4. Cannot emphasize enough. It's so crucial for your programming test too. All right, have a good weekend. I'll see you next week.